All right, so today we're going to look at some more stuff about rational functions. We're going to look at really closely at wholes today. We'll continue our discussion about continuity and asymptotes and zeros as well. So I want you to consider the function x squared minus 9 over x minus 3. I've got it graphed here for you. First thing you should recognize is this does not look a lot like the rational functions we've been graphing. Instead, it looks like a linear function. And the reason why is that if you factor x squared minus 9, which is x minus 3, x plus 3, you'll notice that that reduces with the x minus 3's to become just x plus 3. So how is this similar to y equals x plus 3? Well, it's similar. So I'm going to say f is similar to y equals x plus 3 because it is y equals x plus 3 after we reduce. But there's a very important difference. So if I plug in 3 for x in f of 3, well, let's figure out what that is equal to. Well, if I plug in 3, I get 3 squared is 9. Minus 9 is 0. 3 minus 3 is 0, which is undefined. It doesn't equal like 1 or something like that. No, it's undefined. Anything divided by 0 is undefined. But for y equals 3 plus 3, I'll call that y of 3, is equal to 6. So the important way they're different is that they have a different result when you plug in x equals 3. If I plug in x equals 3 to the original function, I get nothing. I get undefined. If I plug it into the line y equals 3, I would have gotten 6. So what that means is on the graph, there is an infinitely small hole. We typically draw it with this big circle, but in real life, you wouldn't actually be able to see it. It's not like it's got this dimension to it. It's just a hole where the graph doesn't exist. So that's what we'll call it. F has a hole at x equals 3. Now, the y-coordinate of the hole is also important, which is 6. But for this class, we're going to limit our discussion to just stating where the x-coordinates of the holes are. We'll leave finding the y-coordinates later. It's not... It has important applications, but not so much to us right now. All right, I want to go ahead and take a look at a graph of this. I think it's worthwhile to see how this would work out on a graphing calculator. We'll use the Desmos system again. If it'll load. Okay, so we're looking at f of x is equal to x squared minus 9 over x minus 3. Now, just to confirm, f of 3 is in fact undefined. And I want you to see that if I try and drag a point, see I can trace the curve over to x equals 3, we're going to see this thing disappear at some point. Oh, I went too far. There it is. And that's kind of the representation of the hole there. Okay? It becomes really important in calculus, so we want to have this concept down now. All right, so let's just practice doing the algebra to find the x-coordinates of any holes that might occur. If there aren't any holes, then we don't worry about it. All right, so on A, I'll factor. This factors as x minus 4, x plus 4. Now, because the top is the perfect opposite of the bottom, these will reduce to negative 1. Okay? But be careful. Some people are actually overusing this, and they're doing things like 4 plus x and x plus 4 make negative 1. They don't. That's just 1. But 4 minus x and x minus 4 is negative 1. But anytime you cancel the same thing from top and bottom, you usually get a whole. For now, I'm trying to keep things simple, so I'm keeping it to where every time we cancel, that is the x coordinate of a whole. But I do want to tell you there is a case where that doesn't happen. If I had another x minus 4 in the denominator, then it would not be a whole. But because I'm canceling 4 minus x and x minus 4, there is going to be a whole at the 0 of that factor. And the 0 of x minus 4 is 4. Okay? So I hate saying absolutes, but I think I can say it absolutely. In this class, in this year, if you cancel the same factor on top and bottom, that factor is what gives you the whole. Okay? I may have an example where that's not the case, but I would have to have another factor down below still of x minus 4. All right, let's try letter B. I'm going to factor the top and bottom. And this will factor as x plus 6x minus 3. So again, we have the same factor on top and bottom. Do you see it? Therefore, I can reduce it out, and I didn't on the last one, but I should really write this as x over x plus 6 with a whole at x equals 3. So that's what we're saying. We're saying this graph here, pretty complicated looking thing, is actually the same as this graph here, but with an infinitely small whole at x equals 3. It's the 0 of x minus 3. It's what makes x minus 3 equal 0. So if that was an x plus 3, it would be a negative 3. Because you have to add it to the other side. Okay. A whole is called a removable discontinuity. Because while the function is not continuous at the whole, if the whole were plugged with a single point, the function would be continuous, thereby removing the discontinuity. I don't know how much y'all have talked about discontinuity. It used to be talked a lot in Algebra 1, not so much anymore. It is really an important concept in a calculus class. So we don't need to go too deep into what exactly a discontinuity is, but we can go with a basic working definition. That is that if you were to draw the graph with your pencil, say I gave you a calculator or let you use Desmos to graph on a test, and I said, here you go, graph it. Now trace what you see onto your paper. If you have to pick up your pencil and move it somewhere else, there was a discontinuity. To be continuous means that it goes continually together, connected. You can think of it as connected. So if you look at A, and I ask you to draw graph A, would you have to pick up your pencil to draw this? Yeah, you can't get from down here to up here. So that's called a discontinuity. And I think of this as a big discontinuity, okay? It turns out we call it an asymptotic discontinuity. It is a discontinuity, a disconnect between two sides of the graph that occurs at an asymptote. Asymptotic discontinuity at x equals 3. I want you to write that in your notes because eventually I really want you to know those words. However, for this unit's test, I just want you to be able to identify two things about discontinuities. The x value where they occur and whether they are removable or not. So what kind of thing is removable discontinuity? We just wrote it down. A hole. Anything else is not removable. Okay? It has to be a hole to be removable. And the reason why it's removable is because I could simply place a single infinitely small dot and it'd be continuous. I can't place a single dot here and make this continuous. Okay? Take a look at letter B. This graph has this big break right here. And I like to call them breaks, but they're usually called jump discontinuity. And you'll study some functions that have stuff like this more next year. That's a jump discontinuity at x equals -2. Again, I can't just put a point down and magically fill it in and connect the two pieces. This graph, I talk about a discontinuities when you have to pick up your pencil. Maybe you don't think you have to here, but there's an infinitely thin pickup of the pencil. This is a discontinuity because these two branches aren't actually touching, right? So we have what's called a removable discontinuity at x equals -1. Why is it removable? Because it's a hole. That's what a removable discontinuity is, a hole. And there's a whole part of mathematics. We won't do it this year. It's all about plugging in those holes. Going in there and saying, aha, let me just fill that hole in. Boom, now I can finish the problem. And so we got to identify those removable discontinuities this year. We don't have to fill them in, though. Make sense? Okay. Graphs can have multiple discontinuities. This graph has a asymptotic discontinuity at -4 and a hole at x equals 3. So asymptotic discontinuity, continuity, I'm not spelling it right, at x equals -4. Again, I'm not insisting you know those words yet. But the key is it's a discontinuity. It's a place where f is not continuous, and it's not removable because it's not a hole. It's much bigger than that. But we have a hole at x equals 3, so that is a removable discontinuity at x equals 3. All right. So with that... Oh, wait, I'm not done, apparently. I've got more work to do. And then I know we're doing practice at some point. Okay, we're going to do practice after one more set of problems. Okay. Sounds good. Okay. Okay, so, I see. This is where we're going to bring it all together. Okay? We'll also go ahead and look at a graph of these when we're done just to check our work. But for a Algebra 2 student, given a rational function such as those shown in example 9.3, you should be able to identify the horizontal asymptotes if there are any, the vertical asymptotes if there are any, the holes and the zeros if there are any. Okay? And lastly, we can state the domain. The domain, we're going to have to remove everything that's a discontinuity. We're going to have to remove well, you don't always do that, but in this case we will. We got to remove the x-coordinates of holes. We got to remove the x-coordinates of asymptotes. All right, so here we go. Horizontal asymptote, we look at the degree of the numerator and compare it to the degree of the denominator. The degree of the numerator is 0. The degree of the denominator is 2. So because the degree of the numerator is less than the degree of the denominator, we say the horizontal asymptote is 0. Automatic. If it's big on bottom, the horizontal asymptote is 0. Now what I'm going to do is I'm going to go ahead and factor everything to figure everything else out. That's pretty much the only thing where I'm not interested in factoring it first, is the horizontal asymptote. This factors as x minus 5 and x plus 1. As you can see, no factors can be canceled out of the top and bottom. That means there's no holes. Now I look at the denominator for the vertical asymptotes. So zeros, I'm just making some notes here, zeros of the bottom are vertical asymptotes. Again, only after you've canceled out everything, okay? And zeros of top are zeros. Right? When I find a zero, I'm asking, when does this fraction equal zero? The only way a fraction can equal zero is if the top equals zero. Okay? So vertical asymptotes is when you divide by zero. That would occur at 5 and negative 1. So we have a vertical asymptote at x equals 5 and x equals negative 1. And y'all, those are equations of lines. If you say 5 and negative 1, I don't know that you know that. I can't give credit for that. You have to say x equals 5, x equals negative 1. In the same way for horizontal asymptote, you have to say y equals 0. All right, zeros. Well, there are no x's on top at all, so there's no way the numerator can equal 0. So there are no zeros as well. You can do the empty set. You can say none. You can do the little slash through the circle. Lastly, we're going to state the domain. In this class, our domain begins, unless otherwise stated, with all real numbers. But we got to remove every number that gives me either undefined or imaginary. Well, there are two numbers that would give me undefined, and they're my vertical asymptotes. 5 gives me 1 divided by 0. That's undefined. Negative 1 gives me 1 divided by 0. That's undefined. So it's all real numbers except 5 or negative 1. Those are not allowed. And we've done that kind of thing before, right? Okay. All right, let's go on to letter B. All right, the only thing I really think is easier to do before you factor is horizontal asymptotes. So let's do that. The degree in the denominator is 2. The degree in the numerator is 1. Does everyone understand how I'm getting those values? Okay. The degree of a polynomial is the biggest exponent on x. So that degree there is 2. And that's a 1, so the degree is 1. And we basically have 3 rules for horizontal asymptotes. If the degree on top is bigger, you don't have a horizontal asymptote. You just say none. If the degrees are the same, it's the ratio of the leading coefficients. Okay? If the degree is bigger on bottom, it's just y equals 0. Okay? All right, let's factor it. So I get the horizontal asymptote by looking at the degrees, and then I factor. This factors as x minus 5 and x plus 4. Unlike the last problem, you can see that we are going to have something cancel out. That means we're going to have a hole. We're going to have a hole at x equals negative 4 because I canceled out x plus 4. Technically, we would say that y equals 1 over x minus 5 with the exception that x cannot equal negative 4. So we have a hole at x equals negative 4. We have a vertical asymptote at x equals 5. All right, so we've identified the vertical asymptote at 5. It's not a vertical asymptote at negative 4 because we canceled that. And also because we canceled the x plus 4, there's actually no zeros. Remember, the only way a fraction can equal 0 is if the top equals 0. And there's no x up there to make that happen. So my zeros are empty set.
Wait, I'm so sorry.
Go ahead.
Why on
Pardon?
Like we get zeros for, like we don't have any zeros. Like how do we get zeros?
It's the zeros of the top.
Okay.
So if you try and set 1 equal to 0, it does it. You can't, no solution.
Okay.
All right, good question. And vertical asymptotes is the same thing, but with the bottom. Okay? So our domain is all real numbers except for we have a vertical asymptote, so except 5, and we have a hole, so except -4. Both of them don't work. All right, let's try letter C. Now, again, we want to get the horizontal asymptotes before we factor. So my horizontal asymptotes, remember our rules. If the degree on top and bottom are the same, it's the ratio of the leading coefficients. The degree here is 2. The degree here is 2. And the ratio of the leading coefficients then is what we use. 5 over 1. The leading coefficients are the numbers multiplied to the x with the highest exponent. So that's where I'm looking, is right here. 5 over 1. And remember, it's y equals. It has to say y equals. Okay? Now we'll factor. I think the top factors like that, and the bottom factors like this. Once again, we're going to have a hole in this problem. The x minus 2 factor cancels out. So the simplified version of our rational function is 5x plus 1 over x. But we have a hole at x equals 2. This time we are going to have a 0 because zeros are the zeros of the numerator. If you solve 5x plus 1 equal to 0, you get x equals -1/5. Okay, so we just want to know where this fraction, the way we get zeros is we just set the equation equal to 0. That's our foundation, okay? So when trying to solve this, there's lots of different things you could do. You could multiply both sides by x, but x times 0 is 0. But what I usually tell people is that when you're dealing with just a fraction for an equation, the only way a fraction can equal 0 is if there's a 0 on top. So I just ignore the bottom, no matter what it is. And I solve that, and that's just an easier thing to do, I think. Now, vertical asymptotes occur when you divide by 0. So I look at the bottom. What makes the bottom 0? So just set x equal to 0, and you get 0. So I have a vertical asymptote at 0. So you'll kind of hear me say this little mantra over and over again. Zeros are zeros of the top. Vertical asymptotes are zeros of the bottom, and holes are zeros of both, because we canceled it out of both. Okay? Right, I think I get a... Oh, I got to say the domain. And this is important. A lot of people forget the hole. The domain is all real numbers except any vertical asymptotes or holes, except 2 and 0. And I promised that we would graph these, but you know what? I'll tell you what. Let's just graph that last one, okay? And I'll, definitely I would always suggest graphing any of these to check your work and to better understand it. You're not going to be able to generate this kind of graph by yourself without a calculator. Not currently, that is. And then even with calculus, it's not that easy. All right, so we've got this for a graph here. You can see that I like how it drew a big bold line at y equals 5. You see that horizontal asymptote that occurs from the degrees being the same. The leading coefficient is 5. F of 2 is supposedly undefined, and I think you can, there we go. If I can get it just right, we can see that. And this graph does cross the x-axis. Remember, real zeros correspond to where the graph crosses the x-axis, -1/5 or -0.2 in decimal form. And that's pretty much it. And we can see that this graph doesn't have we need to remove 2 and 0 because they're both undefined for different reasons, right? X equals 0 is a vertical asymptote. X equals 2 is a hole. All right, I'm going to break here for a minute and let you practice on these problems. Okay, so practice 9.1 asks you just to identify the x-coordinates of any holes. So remember, a hole occurs when you cancel a factor on top and bottom. And we were having a pretty good discussion here about the numerator here. When I factor f of x, the denominator, you can factor out an x. But at the top, now if this had been a 4 plus x, I wouldn't be able to cancel anything because of the plus. But this 4x is really two separate factors. And so we kind of talked about how you could even think about them as having their own parentheses around them because they're multiplied. Now, I don't recommend normally doing this, but you can see that because of the fact that they're times, they actually are factors that can cancel out. Since an x cancel out at top and bottom, the x value that would make x 0 is a whole. And so, of course, that's just 0. So we have a whole at x equals 0. Let's try the next one. All right, again, I have an x plus 1 on top. Again, that's one whole factor there. I have an x plus 1 on bottom. They reduce out. And we must have a whole at x equals negative 1. All right, so on practice 9.2, we're just estimating the x-coordinates of discontinuity. So remember that a discontinuity means dis meaning not, continuity means continuous. So in algebra, we say things are continuous if when you are drawing the graph, it's one connected line. There's no hops, skips, jumps, or asymptotes. So on this point here, if I'm tracing this graph, all of a sudden, right here at x equals negative 1, it jumps down here. So that is a discontinuity.
Wait, it's a jump discontinuity, right?
Yeah, it is a jump discontinuity at x equals negative 1. And that's good. I mean, eventually I definitely want you able to recognize those. Okay, so we have a discontinuity at x equals negative 1 for sure. And I heard some of you saying it's a jump discontinuity. It is. The next one we have, though, is an asymptotic discontinuity at x equals 2. And if you just want to say for now discontinuities at negative 1 and 2, that's fine. Or you can label them. But one thing you do have to be able to do is state whether it's removable or not. Yeah, neither one of these are removable. Okay? They are non-removable discontinuities. X equals negative 2 and x equals positive 2. Kind of hard to see, but those are my vertical asymptotes. So those are discontinuities. I'll go ahead and name them. Asymptotic discontinuity. Yep. It's not a word that can possibly be spelled right. Asymptotic discontinuity at x equals negative 2 and 2. If I want to give it even a fuller name, I'd say it's a non-removable asymptotic discontinuity at x equals negative 2 and x equals 2. But, All right. A hole. That is a removable discontinuity at x equals 1. Letter D, we have a jump discontinuity. Yeah, at x equals 2, it looks weird. It's kind of a weird moment here, but it's not a discontinuity. Jump discontinuity at x equals 2. Okay? All right. Looks like you get a chance to do each one of these. We had a little bit of a break, so let's do one together, okay? And then you'll do the other two, all right? So this is the procedure, and aside from like being able to simplify and all that stuff, this is kind of the main idea of this whole unit, is to be able to go through this and identify horizontal asymptotes, vertical asymptotes, holes, zeros of the domain. And
Oh, yeah, let's do C.
um,
No.
I'm gonna do A. C has not got that many interesting things. There's no horizontal asymptote because the degree is bigger on top than on bottom. Go ahead. What's the horizontal asymptote? Yeah, because why? Same degree. And the ratio of the leading coefficients, there's an implied 1 in front, is 1 over 1. So there it is. Okay? That's what you do before you factor. Because if you factor it, then it gets harder to see the degree and harder to see the leading coefficients and things like that. So we usually want to do that first. Now we'll factor x minus 4, x minus 1. And the bottom factors is x minus 4, x plus 4. In this case, I do have a factor that cancels out. That makes a hole right there. So hole at x equals 4. So f of x can be simplified to x minus 1 over x plus 4. And it's fine for me if you just write it like that. If you want to be like super exact, like you're writing in a mathematics scientific journal or something and you really care, you would say x not equal 4. That tells people there was a hole there. Okay? All right, now let's look right here at the top. Whatever makes the numerator 0 is a 0. So, yeah, so we have a 0 at 1. And I just put that in, that's a value, and I put it in set notation. Whatever makes the denominator 0 is a vertical asymptote, and that's a line. So you say x equals, and that'll be negative 4. So we have a hole at 4 because x minus 4 got canceled. We have a 0 at 1 because the numerator is x minus 1. And we have a vertical asymptote at negative 4 because the denominator is x plus 4. And our domain is all real numbers except for the locations of any holes or vertical asymptotes, except x equals 4 and x equals negative 4. That's right. And I think that's it. So I'm going to leave you to do B and C. All right. We have x minus 2 over x squared plus 8x plus 15. And I can factor this. And actually, I forgot to state the horizontal asymptote. I actually like to do that before I factor. The degree on bottom is bigger than the degree on top, so that means it's y equals 0. You don't have to compare anything. If the degree on bottom is bigger than the degree on top, horizontal asymptote is y equals 0. In this case, you'll notice that we were able to factor it, but nothing canceled, so that means there's no holes. You only have holes if something cancels. Vertical asymptotes are the zeros of the bottom. So the zeros of the bottom are x equals negative 5 and x equals negative 3. The zeros are the zeros of the top. So at 2. And in our domain, we need to start with all real numbers, but we need to remove the x values of any holes or any vertical asymptotes because it's undefined there. So except in this case, except the vertical asymptote at negative 5 and negative 3, they made the denominator 0. All right, let's take a look at letter C. The degree in the numerator is bigger than the degree in the denominator, so there's no horizontal asymptote. I can then try and factor, but this actually doesn't factor. Don't fall for the trick of thinking this is like x plus 2, x minus 2. It's not, because of the x squared plus 4. That means it doesn't factor. The zeros, the 0 at the top is just 0. Because if I set 4x cubed equal to 0, I get x equals 0. The bottom can never equal 0. X squared plus 4 never equals 0 for any real number. You get, if you solve it, you get plus or minus 2i. So there are no vertical asymptotes. There's no holes as well. So all we have is a 0 here. And I want to take a look at that right quick so you can see what that kind of looks like. Oh, I'm sorry. Domain is all real numbers because there's no vertical asymptote and there's no holes. So if we look at y equals 4x cubed over x squared plus 4, you'll notice that there's no breaks. There's no discontinuities, nothing but that 0 right there. Okay? Well, it turns out that just because something doesn't have a horizontal asymptote, it can actually have a diagonal asymptote or slant asymptote. So a rational function with a numerator degree 1 greater than the degree of the denominator has a slant asymptote. And to find the equation of the slant asymptote, we have to use long division. Okay? I'm going to go ahead and remove that portion from the test. So we'll just stop there and you can skip that on the homework. Okay? So that should give you a little more time to work on your homework in class and you don't have to do the slant asymptote ones. So we'll stop it there.